All right, so here, let's try to figure out what the Maclaurin series is for each of these three functions, e to the x, sine x, and cosine of x. Except first, let's consider these by a function-by-function basis, and start by considering e to the x. And remember, when we're trying to write e to the x as a Maclaurin series, this is just a Taylor series centered at a equals 0. So we're really trying to rewrite our function in terms of this Taylor series or Maclaurin series, which we can write as the infinite sum from n equals 0 to infinity of the nth derivative. Of this case, it will be the nth derivative e to the x, evaluated at 0, since this is a Maclaurin series, divided by n factorial, all times x to the n. Again, a equals 0 for Maclaurin series. So what the name of the game is going to be is we need to just compute a bunch of these derivatives and divide by the corresponding n factorial and figure out what each of these coefficients are for e to the x. So let's go ahead and start doing this now. And the way that I like doing this is making a table. So make a table of n, the nth derivative of the function, I'll just say the function at x, the nth derivative of the function evaluated at 0, again because this is a Maclaurin series, and then finally putting it all together for that coefficient itself, the nth derivative at 0 all over n factorial. So this is our table, and let's go ahead and start computing derivatives. So we'll consider the first couple terms, say 1, 2, 3, and maybe the fourth term. So the 0th derivative of e to the x is just the function itself, e to the x. So if we evaluate e to the x at 0, well, that's just equal to 1. So the n equals 0 term is just taking that 1, dividing by 0 factorial. So the first coefficient is just 1. Okay, the first derivative of our function, well, the derivative of e to the x is still just e to the x. Evaluating again at 0, that's still 1. So we have this first derivative all over 1 factorial, so that coefficient is still 1 there. In fact, let's actually start writing out these terms by term. So if we're to rewrite what e to the x is, the first term, they'll just write in blue. Well, that was our first coefficient, which is just a 1. And then we have a plus times the second coefficient, which is still 1, times x to the first. And let's figure out what that third coefficient should be now. So, going to the second derivative, well, the second derivative of e to the x is still just e to the x. Evaluating that at 0 will still give us 1, and that coefficient will be that 1 all over 2 factorial. So we can tack that on to the next term. The next coefficient is a 1/2, or 1 over 2 factorial, all times x squared. Let's figure out what the next term is. Third derivative, well, third derivative still e to the x. Evaluating e to the x at 0 still give us 1. And that coefficient will be that 1 all over 3 factorial, considering n is equal to 3 in this case. So we have plus 1 over 3 factorial, x to the third. And now we can go on and continue doing this. Taking another derivative of e to the x, well, that fourth derivative is still going to give us e to the x. Evaluating that fourth derivative at 0 still give us a 1. And that last coefficient for n equals 4 is that 1 all over n factorial, which in this case is 4 factorial. So the next term is just plus 1 over 4 factorial, x to the fourth. And we're at the point now where we've figured out the first couple coefficients. looked at what the exact Taylor series looks like for the first couple terms, and are going to basically recognize that, hey, we're at the point we can pick up on a pattern here. So let's go ahead and pick up on that pattern. And it looks like, well, we're always having an x, the nth term of our series has an x to the n, and that nth term also has a 1 over n factorial. So let's actually just rewrite what we found on the next page. So we have that e to the x looks like a 1 plus x plus an x squared over 2 factorial plus an x cubed over 3 factorial plus an x to the 4th over 4 factorial, and so on. And well, we could very compactly rewrite this as e to the x is actually equal to the infinite sum. Again, this is picking up on a pattern here. So we could write this in a very compactified series notation. That it looks like, well, the nth term is just going to be x to the n power all over n factorial. So the Taylor series, or Maclaurin series for e to the x, is the infinite series from n equals 0 to infinity of x to the n all over n factorial. And another unique thing for us right off the bat is, well, this actually gives us not only the Maclaurin series for e to the x, but this is another way to view the function e to the x entirely. And, well, if we just evaluate at x equals 1, we see something else that's interesting. We have, well, e raised to the first power is just equal to, then, that infinite sum of 1 to the nth power all over n factorial. In other words, we're able to rewrite just that constant e as an infinite sum itself, as the infinite sum of 1 over n factorial. And this thing will also add up to the value of e that we know, 2.717 and change. Check out the next video in which we figure out what the Maclaurin series is for sine and cosine.